Hello everyone, I'm Mariana Lozano and I'm here with Isabel Villarreal. Today we'll be presenting hurricane tracking and intensity prediction. The goal of our project was to take real historical hurricane data and build a system that can forecast the next 6 hours of a storm's position and intensity. This type of prediction is important for decision making, emergency planning, and understanding storm dynamics. And now we're moving on to our system design. We use the NOAA Atlantic HERDAT2 dataset. It's stated up here. And includes our hurricane observations from 1851 through 2024. And each storm is identified by an ID and a name, and every 6 hours there's an entry that includes the latitude and longitude of the storm center, the maximum sustained wind speed, the central pressure when it's available, and because of these real observational data, it comes with some challenges. Older storms often don't have pressure recorded, and some records use placeholders like the negative 999 for missing values. To make this usable, we first parsed the raw text into columns and then dropped rows with missing values in our key features, such as latitude, longitude, wind, and pressure. And after cleaning, we then ended up with about 24,000 usable observations, which was enough to train and evaluate models reliably. And now moving on to our exploratory data analysis. Our EDA plots the wind speed distribution in knots and throughout most of these observations in the lower wind ranges, which correspond to tropical storms and weaker hurricanes. As we move towards the higher wind speeds like the category 3, 4, and 5 hurricanes, the number of observations decreases sharply. And moving to the storm tracks, which is our latitude and longitude, the storm track plot shows the geographical paths of storms across the Atlantic basin, and we see the storms forming in the tropics and moving westward, then often curving north and northeast. This matched the expected behavior of Atlantic storms and helped us validate that our parsing of latitudes and longitudes was correct. And now for our central pressure distribution. This pressure distribution shows that there is a big concentration of storms around higher pressures and fewer observations at very low pressures, which correspond to the intense hurricanes. And for our time series problem setup, this essentially is where each storm is a sequence of observations spaced 6 hours apart. And for each training example, we take the previous 4 timestamps, so that's 24 hours of history, and use them to predict the next 6-hour step. Each input window includes the 4 past latitudes, the longitudes, wind values, past pressure values, and the output is the one set of values for the next time. That includes the predicted latitude, longitude, wind, and pressure.
Once the data was structured as sequences, the first model we used was a baseline regression model. Even though it's simple, the baseline is really important for 2 reasons. It verifies that our data processing pipeline is correct. If the baseline completely failed, it might indicate a problem with the data rather than the model. It gives us a reference point. We can later compare the LSTM performance to the baselines and see whether the extra complexity is actually helping. LSTM neural network model. Our main model is a long short-term memory network, or LSTM. LSTMs are a type of recurrent neural network designed specifically for sequential data. They have a built-in memory mechanism that lets them retain information over time, which is useful for storms because what happened a few time steps ago can still influence the next move or intensity change. In our setup, the input to the LSTM is the sequence of the last 4 time steps, each with 4 features. The LSTM processes this sequence and produces an internal representation of the storm's recent history. A final output layer maps that representation to 4 predicted values: the next latitude, longitude, wind speed, and central pressure. We trained the model using mean squared error as a loss function and used early stopping based on validation performance. Early stopping helped prevent overfitting, so the model doesn't just memorize the training storms, but instead generalizes the storms it has never seen before. The training processes and challenges. First, we split the data by entire storms instead of individual rows. This is really important to prevent data leakage. Next, we applied standardization to all features so that latitude, longitude, wind speed, and pressure were all on comparable scales. Without this, the model had trouble learning and the training became unstable. We also faced a few major challenges. One of the biggest issues was missing pressure values, especially in older storms. This caused NAN values during training and completely broke the model at first. Another challenge was parsing the large text file from NOAA. The dataset is very large and not in a clean table format, so converting it took a lot of time and careful parsing and several debugging passes. Finally, we experienced early NAN training instability, where the loss would immediately become undefined. This required us to carefully clean the data, remove invalid rows, and verify the pre-processing pipeline before training could successfully run. Now for the demo.
And we started by loading the clean data set and then constructing the input sequences and then passing them through the train model. The script then prints out evaluation metrics like mean, absolute error, and average track errors in kilometers. And we can visualize a single storm and plot both the actual track and the predicted track over time. When you look at those side by side, you can see that the model's predicted points generally follow the same path as the real storm, with some small deviations which match the error values we just discussed.
Results. The model is designed to generate next step hurricane position, meaning it predicts the next 6-hour latitude and longitude of the storm. It also predicts both wind speed and central pressure, which together describes storm intensity. On average, the geographic predictor error is about 55 to 60 kilometers. That means the predicted storm center is typically within roughly 60 kilometers of the true position 6 hours later. For intensity, with wind speed errors is about 3 to 4 knots, and the pressure error is about 2 millibars, which are both relatively small errors for short-term hurricane forecasting. We also evaluated the model using R-squared values, which were consistently high. This tells us that the model explains most of the variation in storm motion and intensity and is not just guessing randomly. Future improvements. One major improvement would be adding more environmental features, such as sea surface temperature or wind shear. These variables play a large role in hurricane intensification, and including them would likely involve intensity predictions even further. Another future direction would be developing a real-time forecasting application with real-time data feeds. This model could be used to generate live short-term predictions and show them on an interactive map for emergency planners or the public.
And thank you for hearing our presentation, and we are done now. Thank you.
Thank you.